All right, so let's take a look at number 10. We're going to graph this function y equals, these are absolute value bars, so the absolute value of x, and then we've got this plus 2 on the end. So just a couple of reminders, absolute value graphs are V-shaped. Looks like a V. If there's a number in front of your absolute value bars, that would change the slope of our V, and it could also make that open down if we have a negative value in front of the absolute value bars. The only thing we do have other than the absolute value of x is this plus 2 on the end. So this is going to be a translation of our v. Any addition or subtraction that you have outside of your function, the absolute value of x, is going to be a vertical translation. If it says plus 2, then our graph is going to go up 2 units. So our absolute value graph is at the origin, the vertex is at the origin. The vertex is this point right here or this point right here. Looking over here at these V's I drew. So instead of that vertex being at the origin, I'm going to move that vertex up 2 units. So I'm going to go up 2 units and plot a point right here. And now our A value, the A value is the number in front of the absolute value bars. There's nothing there, so that's like a 1. So I'm going to use a slope of 1. So from my vertex, I'm going to go up 1 to the right 1. And then I have to get the left side of the V, so I'm going to go up 1 to the left 1. Your absolute value graphs are symmetrical, so the left side should mirror the right side. So there's the absolute value of x, and then that plus 2 just shifted the entire graph up 2 units. All right, so now we're going to still talk about our absolute value of x. So describe the translation of our absolute value of x. This is what we call a parent function to this, y equals the absolute value of x plus 3 with that minus 5 on the end. Well, just like what we talked about up here, when we had that plus 2 at the end of our function, that was a vertical shift. So if it's a subtraction, if we're subtracting 5, that is a vertical shift also, but we're going to shift down 5 units. So that's one description of what's happening. Now the other thing is we have inside the absolute value bars this x plus 3. Anything that's in with the x, whether it's in parentheses with x, in absolute value bars with the x, in an exponent with the x, that's going to be a horizontal shift. Our x is our horizontal variable, and this is going to shift our graph horizontally. The one thing that we've talked about is anytime that you have that horizontal shift with the x, we always call that our tricky x. Just a little catchphrase to help us remember when it says x plus 3, you're not going to shift to the right 3. We actually are going to shift it to the opposite direction, to the left 3 units. And those are the only 2 changes from our original function, absolute value of x. We have the x plus 3, so we go to the left 3 units, and the minus 5 in the end is going to shift down 5 units. All right, so number 12, we're going to keep talking about our absolute value functions, but now we're going to focus on domain and range. So the question is, how do the domain and range of f of x equals 4 times the absolute value of x compare with the domain and range of g of x, which is equal to negative 2 times the absolute value of x? So just a couple of reminders on domain and range. So our domain is our input. So domain is the input, and in a function, those are going to be the x values. So if we look at a function, right here is the x. So the question is, what numbers can we plug in for x and then take the absolute value of that? So there's 3 categories to consider. You want to think about negative values, you want to think about positive values, and you also want to think about the one in the middle, which is 0. So can we plug in a negative number for x? Is it possible to take an absolute value of a negative number? Yes, it is. Can you put in a positive number for x? Can you take the absolute value of a positive number? Yes, you can. And then the one in the middle we want to check is 0. Can you plug in a 0 for x and take the absolute value of it? Can we perform this function, the absolute value of your positives, your negatives, and 0? And because you can do all that, we didn't have any restrictions on that. That means our domain will be all real numbers. Now, on a side note, when is your domain not all real numbers? You guys have seen a lot of the domain being all real numbers. Um, let's say instead of an absolute value of x, I change the function to the square root of x. So if you think about numbers that you can take the square root of, can you take the square root of positive numbers? So let's just throw in a positive number. Square root of 9, yeah, that's a positive 3. Can you take the square root of 0? Yeah, you can. Square root of 0 is 0. Can you take the square root of, let's say, a negative 4? Now, if you were to type that into your calculator, you actually would get an error message that says domain error. You cannot take the absolute value of negative numbers. So in this case, our input, what types of numbers can we plug in for x? We can plug in positives, we can plug in zeros, but we cannot plug in negatives. So the domain of this function, square root of x, is not all real numbers because we actually can't have any negative numbers in that domain. So that's a side note conversation just to kind of see what does it mean when you don't have all real numbers for your domain. All right, so next let's talk about range. Range is the output. So the output of your function you can think of as the y values. So when we put in positives, negatives, and 0 for x, what type of numbers do we get back? What would our output be? So when you have an absolute value function, what does the absolute value function do? It turns any number positive. So that's kind of by definition, it will have any number that you plug in, it will kick out a positive number. So when we have the absolute value of x and we get all these positive numbers, and then we multiply those positive numbers by a 4, then you have more positive numbers. So what you're going to find is that the absolute value of x multiplied by a positive 4 will never be negative. What that looks like on a graph, just so we can kind of compare, sometimes it helps to see graphically. I'm not sketching in the right spot. So here's the absolute value of x with that 4 out front, just gives us a skinnier, kind of a thinner v. What you'll notice is we don't have any v down here where the y's are negative. Our v starts at 0 and is just all of the positive numbers. So our range, we have to talk about the y's. All those y's will be greater than or equal to 0. All right, so that's the domain and range of our f of x function. Now let's talk about the domain and range of our g of x function. Well, our g of x function is still an absolute value function. We're just multiplying it by a negative 2, but what kind of numbers are we allowed to input, to plug in for x? Can we take the absolute value of positives? Can we take the absolute value of negatives? Can we take the absolute value of 0? And just like this one over here, yes, you can take the absolute value of any number. So our domain is all real numbers. You can plug in any number for x and perform this function. All right, our range, well, on the last one, it kind of made sense to look at a graph. If we plug in numbers for x and we take the absolute value, we're going to get all these positive numbers. What happens when we take all these positive values and then we multiply those by a negative 2? Well, all these positives by a negative number is going to turn them all negative. So on a graph, what this looks like is if you have the absolute value of x and then that multiplied by a negative 2 out front, your vertex is at the origin, and that negative 2 tells us that our v opens down, and we would go down 2 to the right one, so it's a little bit of a skinnier v. So we can see that our output, our function, we don't have any function up here with the positive y's. It starts at 0, and we have all these negative y's. So the range for this function, we would say, is y is less than or equal to 0. So how do the domain and range compare? Well, they have the same domain. With our f of x function, our domain was or our range was greater than or equal to 0, and with the g of x function, our range had all the y's less than or equal to 0. All right, number 13. Ethan rode his bike to his friend Sasha's house. Then Ethan rode his bike to the library. The graph shows Ethan's distance from Sasha's house as a function of time. So just so we understand what's happening, time is passing, all right? And then what this graph is showing is the distance, Ethan's distance from Sasha's house. So at the start of our time, Ethan is 12 miles from Sasha's house. As time goes on, the distance to the house gets smaller because he's getting closer to her house. So now after 10 minutes, he's only 6 miles away from the house. After 20 minutes, he's 0 miles away from the house, which means he's at Sasha's house right now. This is a tongue twister for me. Sasha's house. Okay. Then as time continues, after 25 minutes, 30 minutes, what's happening is he's riding his bike away from Sasha's house toward the library. So now, because he's riding away from her house, after 30 minutes, he's 6 miles away from her house. After 40 minutes, he's 12 miles away from her house. And now he's at the library. So how many miles total did Ethan ride? Well, he starts out 12 miles away from Sasha's house. He's riding all these miles. When he gets to Sasha's house, he has ridden 12 miles. But then he keeps going. Time continues, and his distance increases as he moves away from Sasha's house, and he rides another 12 miles when he gets to the library. So how many miles did Ethan ride? Well, Ethan rode 12 miles. That got him to Sasha's house, plus another 12 miles got him to the library, for a total of 24 miles. All right, so part B, over what interval is the function decreasing? All right, so what we're talking about for decreasing, could be increasing intervals is as we look at the graph from left to right, where is our function decreasing or going down? I want to point out where it's not decreasing first. Do you see from here to here? Looks like I'm going up a hill. This is an increasing interval from here to here. This is where we're decreasing from here to here. Now, when we give intervals, increasing or decreasing intervals, we have to use x values. So we are decreasing from here all the way to here. So do you see how in between these two x values, our entire function is decreasing? So that's from a 0 all the way to a 20. So that's the interval from 0 to 20. How we would write that is we would say 0 is less than or equal to x is less than or equal to 20. That's an interval that we are decreasing. Our function is decreasing when the x's are between 0 and 20. All right, part C, find the average rate of change. All right, so you guys know, circle average rate of change and write in the word slope. So when we do an average rate of change, we're going to find a slope. We need two ordered pairs to find slope. They're going to give us two x values to use for our ordered pairs. So one x value is going to be 10. We don't know the y value. The other x value is 20. We don't know the y value that goes with that. So if we had the function, we have put these into our graphing calculators before and looked at a table of values to grab these ordered pairs. All we have is a graph right here, but we can get ordered pairs from a graph. So when x is a 10, what is our y value? I'm going to go over, here's where x is a 10. I'm going to go up until we get to our function right there, and I can see that our y value is a 6. So that's that spot right there. When x is a 10, y is a 6. Now when x is a 20, what's our y value? So I'm going to go over to where x is a 20, and I can see, oh, this is where the function is. Our y value is a 0. And now we're going to find the slope. y2 minus y1 over x2 minus x1. So y2 minus y1, 0 minus 6 over x2 minus x1, 20 minus 10. 0 minus 6 is negative 6. 20 minus 10 is 10, and negative 6 over 10 reduces to negative 3 over 5. And we also can turn that into a decimal. I think I would take both answers. If this was on the exam, multiple choice, just see if they're looking for decimal answers or fraction answers. So we could say negative 3/5, or we could say negative 0.6 as our average rate of change. All right, last question. We have graph a function. So do you guys remember these functions that have a couple parts with some, what do we want to call these over here? Tells us what part of the line to keep. So this is our piecewise function. A piecewise function means we're going to draw a line, but only keep this piece of it. We're going to draw a line and only keep this piece of it. So one thing we notice is we have two lines, f of x equals negative x plus 3 and f of x equals 3x minus 1. So let's just start with our first one. F of x equals negative x plus 3. So I'm just going to go ahead and write, that's the same thing as y equals negative x plus 3. Our slope is negative 1, and the y-intercept is at 0, 3. So let's go ahead and draw the line. Use a pencil if you guys are not, because we're going to erase part of our line. We're going to go up to 3, that's our y-intercept. Our slope is negative 1, so down 1 to the right 1. And we're going to draw in this line. All right, now because this is a piecewise function, we actually don't want to keep the entire line. We only want to keep the line where all the x's are less than or equal to 1. So it's helpful for us to draw in kind of a divider line where x is a 1. Well, here's where x is a 1. So why don't we put in that line where x is a 1? That's where x equals 1. So we want our line negative x plus 3 only where the x's are less than or equal to 1. Less than this line is going to be the left side over here. So we want to keep this half of our line. We're going to erase the right side. So grab your eraser. This is part of our line. You can see we already have an arrow on the left side over here. There we go. So we need a circle here. It's either going to be an open or closed circle. Because it's a less than or equal to, we are going to put a closed circle. We use closed circles for our or equal to inequalities. All right, now because this is a function, I know that the other part, the other line, should be over here. If we did this one correctly, I'm not going to have two lines on the same side of that divider, x equals 1. But let's go ahead and talk about our second line. We have y equals 3x minus 1. Our slope is a positive 3, and our y-intercept is negative 1. So because our y-axis is over here, we kind of borrow from it. I am going to plot this point at 0, negative 1. I'm going to end up erasing it because it is on the wrong side of our divider line. And I'm going to go ahead and plot some points for a slope of 3. I'm going to go up 3 to the right 1, up 3 to the right 1, up 3 to the right 1. Now, if I were to draw in this line, well, not if I were, here I am drawing in our line, we're not going to keep the whole line. We're only going to keep our line where the x's are greater than 1. Greater than 1 is going to be on the right side of our divider line, so I am going to erase the left side of this line. All right, now open or close circle. This inequality says greater than 1, so we would have an open circle, but if you notice, this open circle would be right where this closed circle is. So if you have an open and a closed circle in the same spot, the closed circle wins. You're just going to have a closed circle right here. If these were in different spots, you would see the open circle somewhere else. And there's your piecewise function.